from the very beginning, let's go back to August and bring up something that I told you way back then. The purpose of a graph is to provide you with information about something that's happening in the real world. That's what it's supposed to do. It's supposed to give you some information, and you're supposed to be able to glean from it some conjecture. So I want to remind you or show you a graph that we had way back at the beginning of the year, probably the first kind of graph I presented to you when we were first learning the vocabulary of physics. It looked just like this, and it said position versus time. Units were given, most likely, and I think this was labeled A and B, and somewhere around here was a time, like say 5 seconds. Now, every graph that you are that you will be presented is attempting to tell you something. You should, when presented with the graph, ask yourself what is being displayed. You could turn this into a simple fill in the blank. Something like this is comparing blank with blank. But it's probably better if you come up with a sentence that describes what is being demonstrated. Do that before you read the question. You're going to be given graphs on the exam, and you've been given graphs in your multiple choice, and a lot of times you just try to blow through it. And if you're like anything like first period, you'll say things without thinking them through. For example, is there ever a time on this graph when the two objects have the same speed? I can just look real quick and I see a few things like this, but you don't know what this graph is displaying if you said yes. And it's because of that I think you guys have problems. You jump at things, and they're intentionally going to try and trick you. Now, it's not intentional, I guess is the wrong word. They're going to try and put things in front of you that they know you guys will answer incorrectly because you're not thoughtful about what's being displayed. So, let's try and be thoughtful about what's being displayed. And let's go one step further and also add to it, what other information does the graph have that is being communicated to you that might not be just what the graph is displaying? So right now, consider these things. What is the graph displaying? Consider the meaning of the slope and the meaning of the area. If you don't remember how to do those things, what is being displayed is a sentence that describes specifically the display of the graph. Something about the vertical axis and the horizontal axis, something's being communicated. To deal with the slope, you just take what's on the vertical axis and divide by what's on the horizontal axis, and also do the same thing with the units. For area, again, you take what's on the vertical axis and multiply by what's on the horizontal axis, and do the same thing with the units. Your goal is to see if the units or the slope or area, if it kind of communicates some other meaning. You said the slope is the velocity and the area is the displacement. One of those two things is true. So when we look at the slope and the area, we do take a look at the units and see if the units match up with something that we already know about. Meters per second, definitely velocity. Meters times second, not displacement. Displacement would just be in meters. So I don't know that the area of this graph has any meaning because I don't know of anything in our equation sheet or in our unit system that's meters times seconds. So I think I'm going to throw away the area as not being useful, but I do think the slope is the velocity. So we'll start with that. We tested the slope and we tested the area. We have some information we can walk with. I think we're going to say the slope is the velocity. But what you didn't actually answer was, what is this actually displaying? Can somebody offer me a one-sentence explanation of what's being displayed? Go ahead. Should have said a name. That's okay. Go ahead, David, louder. Let's see what you said. I think that's okay. I'm looking for simpler words, though. Something that you could communicate to a child. Yeah. That's more information than we need. This graph just what does it show? Simple. Go ahead.
How far an object travels over a certain period of time.
So all of these things are things that you are interpreting from the graph. You're making assessments of the graph. The graph just tells you where the object is at any moment in time. Right? It says where. Position is where. And any moment in time. Now, you've made several assessments because of that. You've talked about change in the position. Well, I could have a graph of an object that's position versus time that shows it doesn't change, right? I mean, if I just drew this in, object C. Let me make sure. There, object C. Does object C change its position ever? No, but this is still a graph that tells me where object C is for every moment in time. It also tells me where object A is and where object B is. It's a position versus time graph. It shows you where something is. I want an overview. Now, yeah, you could start to tell me more information. A position versus time graph could tell you other things, like it's traveling away from something or towards something. You could get that from a graph, but that's starting to interpret the actual data points. That's more than just what does the graph display. A lot of times you don't stop and ask yourself, what is the graph showing? You jump into trying interpreting it, which is why several of you got the question wrong. When does the object have the same speed? These objects never have the same speed. Not once. Something is happening at 5 seconds, but they don't have the same speed at 5 seconds. But you jump at those kinds of questions because they feel like they're just easy. And it's obviously something's happening there. But do they ever have the same slope? If the lines never have the same slope, they never have the same speed. Go ahead.
So, like one of the Maya Cube questions, there was something where it was asking about where we have the same velocity as each other, and it was kind of like a straight linear line, and then one that was kind of curving.
Yep, we're going to take a look at one of those. That's our second example.
Okay. Is that just to find that would be slope as well? Because I was confused how because I didn't pick what the right answer was. It was my problem.
All right, well let's make it through this one, and then we'll do one like what you're describing. Is that good for you? All right, so A and B never have the same slope, so they never have the same speed. Something is happening at 5 seconds, and I hope you know what that is. But it looks like A started behind B. Would you agree with that? I'm looking at time 0. A started behind B. B doesn't travel as far in the 5 seconds as A does. Can you all see that okay? So that's another thing to consider. A is traveling faster, so it travels farther in 5 seconds than B does. But A is passing B at 5 seconds. But is there ever a time in this graph that A and B have the same speed? No. So let's talk about your question, because I think your question is well timed for what we want to do next. So I'm going to change it just a little bit. Let's put one of the cyclists back up there. Cyclist A, and then cyclist B. Okay? This gives us some place to start. We'll say that this is 2 seconds, and this is 10 seconds. Now, what is being displayed? Same as before. Where the object is at every moment in time. But there's also other things we could get from this information, can't we? Does cyclist A and cyclist B ever have the same speed? Now, does cyclist A speed ever change? No. Does cyclist B speed ever change? Yes. Is cyclist B speed increasing or decreasing? Increasing. The slope is becoming steeper. Correct? In fact, if I was to take a look at the slope, I think cyclist B starts with a slope that's almost 0. So maybe cyclist B, when we start observing, started from rest and wasn't moving at all, and then saw cyclist A coming at him and started to speed up. Would you agree with that? A reasonable assessment? And then, is there ever a time, I'm trying to make these two lines parallel. Is there ever a time when the slope over here is the same as the slope over there? Yeah, I think so. In fact, I'm arguing that right about where I have that red line is probably where cyclist B and cyclist A have the same speed. You guys agree with that? It's only for an instant, isn't it? Because cyclist B is speeding up all the time. Cyclist A has the same speed all the time, but it looks like to me, somewhere between 2 and 10 seconds, cyclist B finally has the same speed as cyclist A. Cyclist A is ahead of him though, right? You can see that too, because it looks like they have the same speed right here. Would you kind of agree with that, where I put it? At that moment though, cyclist A is further away. It's further ahead, farther away from the origin. Will cyclist B ever catch up to cyclist A? Yeah. Do they have the same speed when cyclist B catches up to cyclist A? No. At that point, who's going faster, B or A? B. Does that answer kind of the question that you had? Now, the truth is, I could have kind of crazy cyclist C. I think cyclist C, I don't know what he's doing. But would you agree that cyclist C probably has the same speed as cyclist A a couple of times? Any place where the graph would be the same slope as cyclist A. So maybe over there, and maybe right here, and maybe right there, maybe right here. But there's times when he's speeding up and times when he's slowing down. He's very erratic. Would you agree? He's all over the place. So cyclist C is kind of crazy, but he has the same slope as cyclist A several times. All good so far? Position versus time graph tells you where the object is for every moment in time. You can get from it a reasonable understanding of how their speed changed or stayed the same. So the slope of a position versus time graph is velocity. The area of a position versus time graph has no meaning. So, moving right along, because we did that for like a week, and then it was time for us to put on our big person pants and hit the real graphs, stuff that had more information. So, I don't know that you will remember these, but okay. This is a velocity versus time graph. Talked about it at length. Take a moment and assess what is being displayed. Maybe ask yourself what is not being displayed. And meaning of the slope, meaning of the area. So, we want to offer what is this graph showing us? Go ahead, Camilla.
It's showing the velocity of something as time.
Right, it's showing us how fast something is going for every moment in time. But it tells us more than just how fast something is going. What else does it tell us besides how fast something is going? No, just what it's showing us, not interpreting. It gives us more than just how fast. It gives us direction. It tells us whether it's going forwards or backwards. So it tells us how fast and in what direction an object is going for every moment in time. All right, can somebody tell me what the meaning of the slope is? Lance?
Would the slope be acceleration?
The slope is acceleration. Can somebody tell me what the meaning of the area is? Go ahead. Displacement. So this graph shows us the speed and direction of the object, but we can interpret from the graph the acceleration of the object and the displacement of the object. Is there anything that this graph can't tell us? There's some things that this graph can't tell us. I'm not sure if you remember what it is. Does this graph ever tell us where the object is? can't tell us where the object is. It can tell us how much the object moved, but it doesn't know where it started. So one thing that's left off, because it's not a position graph. So although we can find out information, there's information that is missing. So, is this object ever stopped? So Corbin, when is it stopped? 5 seconds. So let's ask some more difficult questions. All right? Is the acceleration ever positive? So I have more confusion here because people are doing this or this. Is the slope ever positive? No. So the acceleration is never positive. In fact, we could argue right now, is the slope ever changing? No. So this object has a constant negative acceleration. Is the object ever slowing down? It has a constant negative acceleration, but is the object ever slowing down? See what I mean when I say you guys have a hard time with this stuff? But if we look closely at this graph, its velocity starts at some positive number here. I picked 1 point because the graph tells us how fast and in what direction the object is going. So right now, it's going something positive right there. Is the object's speed faster or slower at point 2 compared with point 1? Slower. So did it speed up or slow down between point 1 and point 2? Slowed down. In fact, at point 3, what's its velocity? 0. So I think we could say pretty clearly that it's slowing down. Is it still slowing down at point 4? Whoa. What do you mean? The acceleration is negative. But doesn't that mean slowing down? No, acceleration doesn't tell you slowing down or speeding up. It tells you how the velocity changed. The velocity is becoming a more negative number. It started at a positive number, but the velocity is becoming a more negative number. Once I reached a velocity of 0, the velocity became a more negative number, so now I have a negative velocity. It just means it's going backwards. And in fact, at 5, is it going faster or slower than it was at 4? Faster. Is it going forwards or backwards? So a negative acceleration doesn't mean slowing down or speeding up. Slowing down, speeding up is conditional. You have to look at the conditions. This graph told you. It tells you everything about that. In fact, it tells us more than that because, as you said, this area, an area is the part between the curve and the horizontal axis, assuming the horizontal axis is a 0. Is that area positive or negative? Positive. So it traveled in a positive direction. And this area, is it positive or negative? So this has to be a negative displacement. So, with all that wonderful talk, and you guys knowing all these wonderful things, and you're quite capable people, assuming at t equals 0, x equals 0. Plot x and t. Can you make the position versus time graph? Let's say that this is 5 seconds. What would it look like? Where is the object at every moment in time? A position graph can tell you velocity, correct? We just talked about it. How do you determine the velocity from a position versus time graph? Slope. Okay. So at the point marked 1 on the velocity graph, is the velocity positive or negative? Positive. Is it a big number or a small number? Compared to everything else, it's a big positive number. So at 0 on your position graph, the slope should be a big positive number. right? Position of slope. All right. Is the velocity ever 0? Yes. When? 5 seconds. Okay. So at 5 seconds, the slope of your graph has to be 0. Has to be, right? Going from time equals 0 to 5 seconds, was there a displacement? Yes, right? There's a positive area. So I had a positive displacement, which means I am somewhere in front of where I started. And at that moment, I have a slope of 0. Aren't these are all just reasonable deductions, right? You guys tend to want to just jump at it, but you don't have to. Just ask yourself some reasonable questions. After 5 seconds, is my slope going to be positive or negative? Negative. In fact, it looks like it's going to mirror the same thing that just happened to get to where I was. So probably over, say, here, am I going to have a positive or a negative slope? Negative. I know I'm going to be coming back because I know I have a negative displacement, right? Because I have this patch of area that's negative. So I'm expecting a slope that's like that. Can you connect this with some kind of smooth curve? I don't know that you're going to have to do this on your exam, but whenever you guys have had to make a graph on your exam, you guys tend to try and jump at it. Like they've given you information to use. Use it. What's being pictured? If it's picturing where the object is, then what was the object doing while it was moving? It was slowing down and speeding up. Put those things in there. All has meaning. Now, we have limited time to do all this. But obviously, we could do other examples of this. I've given you one, but I want to talk about other graphs now. Graphs that we've had less experience working on. Because the position versus time graphs, go back to your homework. You had lots of it. How about this one? This one's going to show you a lot more than you probably realize, which is why I want to get to it. This graph, it's amazing what you can be given with this graph. So, did you come up with a description? What are we displaying here? This is the force on an object over some time interval. This is how much pushing was done to something over some time interval. Was the force a constant? No, the force was changing. The force started at 0 and went up to 10 newtons. That's important because that tells you so many things. So many things are just in that one idea. Because net force equals ma. Was the acceleration constant?
Yes.
Nope. No. If the force wasn't constant, then the acceleration wasn't constant. So no, there's not a constant acceleration. That means stuff. Not constant acceleration means no motion equations can be used. All of your motion equations assumed a constant acceleration. This one can't do it. Did you test slope and area? Slope is force over time, newtons divided by seconds. Area is force times time, or newtons times seconds. Do either of these have meaning? Yes, one does. Which one? What is it? That's right. This is impulse. Impulse is change in momentum. The area of this graph has meaning. Slope doesn't. Area does. things this graph can't tell you. Can't tell you where the object is. Doesn't contain it, doesn't have it. Can't tell you how fast the object is traveling. And actually can't tell you the acceleration unless you have the mass. But if you were told that it started from rest, you could figure out what the object's velocity is after 2 seconds because you have the change in momentum. You could also figure out things like kinetic energy because you would have mass and you would have velocity. We'll pick this up tomorrow right here. At the very end of yesterday, we were looking at this specifically and talking about a force versus time graph. Now, a force versus time graph tells you how much force was applied to something during some span of time. I failed to mention something yesterday that I think should make some appropriate sense to you right now. This could be effectively nothing happening. You could press on the wall and press harder and harder and harder for 2 seconds. And you'd get this graph if we were talking about just the force you applied to the wall. That would be kind of a meaningless graph, but you could do it. Or I could just grab the force sensor and squeeze it for 2 seconds and get this graph. Have I really done anything? No. This makes way more sense if I had written net force here. That's what would make this net force equals ma. So be aware that if you just graphed or plotted a force acting on an object for 2 seconds, it probably wouldn't make much sense. But if it's the net force, then the area under that graph is impulse. Now, I need to be careful here because I don't remember exactly what I said in this class, but impulse tells you how much the momentum changed. Remember the things that it can't tell you. It can't tell you what the momentum was. Right? It can tell you how much the momentum changed, but not what the momentum was. If you do know the mass, it can tell you how much the velocity changed, but it can't tell you what the velocity was. So it's just like a velocity graph can't tell you where the object is. It can tell you how much it moved. A force graph like this can't tell you what the velocity was. It can just tell you how much the velocity changed or how much the momentum changed, which means can't tell you kinetic energy unless you know one of the velocities. It can't tell you kinetic energy unless you know one of the velocities. Do some kind of data analysis that's going to involve you plotting data or you interpreting somebody else's set of data. That's very likely. We've talked about a few different scenarios here, and that's why day before yesterday we did linearization of data to have remind us about the practice that we've done in the past, but also to make sure you understand that's a quite reasonable thing to have on the exam. The thing I would want to add then is threefold, and I do want to remind you that it is quite plausible that you will have to. So I want to add a couple of things that although we've talked about, they are things that may be less fresh in your memory. They didn't come up as often. And then at least one that we've not seen before. All the other graphs we've had so far have been some instance of time, right? They told you something that happened for a couple of seconds or a couple of minutes. It was something that we observed. That's not this, right? This observation is different. So you may have to add more to be able to describe this observation. So could you add a little more?
As the object moves away, the force on the object gets bigger.
See, I think this one is hard to describe because does that sound like something that makes any sense to you? It does look like to move an object, I have to push harder. Right? Is that what you're seeing here? That if I move the object to here, I have to push this hard. But to move the object to here, I have to push this hard. So I clearly have to push harder if I want to move the object further. Now, you made this graph. First semester. I don't know if you remember that far back, but we did a lab like this where we hung weights on a spring. Do you remember? And you measured how far the spring stretched. That's what this is. You put a weight on a spring, and what happened to the spring? It stretched a little bit. If you put a little more weight on it, what did it do again? It stretched a little bit further. Put a little more weight on it, stretched a little bit further. Now, to be honest, not many people did this lab because it was like the day before Thanksgiving. But we did this lab. Now, when we did this lab, this is what the graph looks like because it's linear. If you add, we know for a spring, the force from a spring is proportional to the displacement. Yeah, it's negative, but let's just realize that if I take away the direction part, if I hang more weight on a spring, it stretches the spring more. That's what this is showing. That's why it's harder to describe these because it's not about time. It's about moving something and how much force is necessary to do so. I want to show a couple of things here, but first, let's say that this represents position X. Like I move the object from the origin to X. You guys are smart, but you often have difficulty with abstraction. So this point right here is how much force is necessary to move the object to a distance X. Can you tell me what that force would be? It's funny because it's actually right in front of you. If the slope of this line is k, because this is y equals mx plus b. If the slope of this line is k, because it's a straight line, this point would have to have a force equal to kx. Right? That's what it is. We said it's a spring, and the force is equal to kx. So if I move the object a distance x, then that point the force has to be kx. If I move the object a distance, say, x2, then what would the force be here? kx2, that's right, kx2. If I only moved it a distance, say, x1, what would this force have to be? This really isn't that hard. So I'm trying to realize that this is how much force it takes, but this is a linear graph. Now, part of the reason I'm bringing this up is to show you something. But you have to buy into the idea that it's just a linear graph. The whole idea of a linear graph is it pairs two numbers. I am telling you a force for every position. It's related by this function, kx. So you tell me how much you want to stretch the spring, I'll tell you how much force it takes to do so. Does that make you following so far? Well, let's stop and remember that whenever we have a graph, we should check to see if the slope makes any sense or if the area makes any sense. In this one, the area makes sense. The slope doesn't. This is going to be force times not position, but the area under the graph would be change in position from one place to another, so that would be displacement. Do you have something in your equation sheet that's force times displacement? Work, that's right. The area under this graph is work. Now, there's a lot to unpack here, so let's start with the basics. Let's just look at the spring. I want to show you something. What kind of shape is this? Is it clearly a triangle? 1/2 base times height? So base is x, and the height is kx. Bring out 1/2, so 1/2 kx squared. Does it look familiar to you? So the work done by compressing a spring or pulling out a spring is equal to the potential energy in the spring. All things we would kind of expect to happen. So first, area under a force versus position graph is the work done on an object. Okay. The next thing, what if this was not you just hanging weights on the spring? I say that because if you were hanging weights on the spring, the net force was 0. There was weight downwards and spring upwards. So the net force was 0. Our object stretched the spring, but then we let it go. Did it move after that? No. What if I pull something back against the spring and let it go? What does the spring do? Yeah, it's going to launch the object, right? So if the only force was the spring, then this would be a net force versus position graph. Net force means there's an acceleration. On a net force versus position graph. So I'm just going to change just a little bit, but you should add this to be something different in your notes. In a net force versus position graph, it's not just the work, it also equals the change in kinetic energy. Now, it doesn't tell you how much energy the system has. It tells you how much the energy changed. If you want to know how much energy the system has, you have to be given either the starting or final energy. So this is another case in which it just tells you by how much something changed. To know anything else, you would need either the starting energy doesn't tell you the starting energy, doesn't tell you the velocity, doesn't tell you the mass. None of these things can be conveyed with this graph. If you were given one of those, you could probably determine other stuff, but it doesn't give you those. So with that being said, you would not be able to know the momentum. These are things you would not be able to tell from this graph. All right? Got a few more. We're doing good so far? All right. I'm scared to show you this next one. I never did this in class because I thought it was kind of dorky. And to be honest, I probably should have, because AP does do this from time to time. I don't do bar graphs in this class, but I want you to think of something for a moment. You guys you have imaginations. Like many of you are imagining not having to be in physics anymore. If I put a 2-kilogram rock at the top of a 10-meter tall tower, how much potential energy would it have? All right, simple numbers, right? MGH, so M is 2, G is 10, H is 10. So how much potential energy would it have? 200, yeah. I was not asking a hard question. So if I put here 200 joules, I could make a bar graph that showed the amount of energy the system had. Right now it has 200 joules of potential energy, and how much kinetic energy? 0. So this would be when the rock is there at state 1. So I drop the rock, and the rock falls, say, halfway down the tower. So this is state 2. It's moving now, right? It has a velocity that's this way. How much potential energy would it have right now? But the total energy has to be 200. So where's that other energy going? I think these are silly little bar graphs, but they've shown up on exams before. Like you're having to say which of these bar graphs would represent the energy in the system right now. Well, this would be the bar graph that would represent the energy in the system right now. I don't think this takes higher order thinking skills, but this is supposed to be how people who are visual learners visualize energy. So maybe if you're one of those people, like you fill up a big cup full of something and you can pour some of that into the potential energy cup or the kinetic energy cup, but you're never going to get more than what was in the original cup. Does that make sense? That's what they're trying to teach here. So what if we say, okay, now it's down here and it is 2 meters from the ground. How much potential energy would it have now? What's that? Well, it would have less. How much? MGH, good job. 40. All right, so now you realize the potential energy graph has to go down to 40. Well, that means the kinetic energy graph has to be enough to keep it at 200. Does that make sense? I think these are kind of silly. There was an FRQ on it last year. I think so, yes. Because it just seems so silly. But it is, but if you've never seen it before, it was like, this is the potential energy graph. This was the energy graph, and it just showed 2 bars. Would you know that you would add this up to get the total energy? I would think so, because it seems kind of childish, but yeah, I didn't get into this at all, and I never would have thought they would have given an FRQ on it, and they did. So there it is.
It was on the MCQ.
I know, I put a few on there.
Oh,
Were they particularly hard?
No.
No. So, but I want to make sure, I try to be thorough. All right, so this next one, though, is kind of a higher order thinking one. And this is the last one. I don't know if you'll be able to do this or not. I've never seen this on the AP exam. It's not an unreasonable thing, though. What's the equation for the potential energy of a spring? Yeah, we just talked about it. So 1/2 kx squared. What would that look like in this graph? If I graphed this, what would it look like? And every time I've asked that question, I've gotten this blank stare from students. And I don't understand why, because you've all had algebra. Now you have a calculator, you can just plug it in to see what it looks like. But we have limited time. Y equals ax squared plus bx plus c is something you do know about. So when I say this, you understand I am also saying this. Right? They are the same thing. But for whatever reason, students don't make that leap on their own. So have I helped you make the leap that this is the same kind of graph? What would this graph look like? All right, so it'd be a parabola, right? Not great, but not terrible. Better, more circular. There, is that more parabola-like on one side? It's the other side that I always have difficulty with. Eek. This is just so hard to make it consistent. All right, we're sticking with that one, whether I like it or not. That's the one. Now, let's say this represents 10 joules there. Okay. And let's say that I tell you that your system only has 4 joules of energy. What that would mean is this yellow line, which crosses at the 4 joule mark, represents the amount of energy in the system. That means this point and this point are the boundaries of the system, meaning the object can't be here because it would require more than 4 joules of energy to get there. Right? If I say the object only has 4 joules, then it'll never be there because that requires more than 4 joules. Do you guys understand that idea? This isn't anything complicated. This is a spring. So that means that it's going back and forth between 2 places. Right? We know that. You pull the spring back, it just goes back and forth, and it goes back and forth the same amount on each side. This is what the graph would look like that would tell you that. So let's say when I pulled the spring back 6 centimeters, that gave it 4 joules of energy. Well, I know that this one over here is going to be negative 6 centimeters because it goes back and forth the same amount on both sides. It's a parabola, so it's symmetrical. But that also means there'll be a time when the object's at the 2 centimeter mark, right? It's going to pass by that point. When it's at the 2 centimeter mark, this represents how much potential energy it has. That also means that this represents how much kinetic energy it has because the total energy is 4. Does that make sense? All right. So it's the same thing. It's just a graph that doesn't conform to something you know about, but it's still an energy versus position graph. So if you have a finite amount of energy, say 4 joules, this defines where the object can be. It can be any place where the object has less than 4 joules of energy.